okay? Remember, ethers are our functional group. That's kind of the start of our discussion, where we have our oxygen being sandwiched between two carbon atoms. And these are generally pretty boring functional groups. Generally speaking, when you encounter ethers, you encounter them only as relatively non-polar solvents. We like them because they're pretty easy to get rid of. They got really low boiling points, right? So if we need to boil off that solvent in order to get our pure substrate at the end, it's pretty easy to do. A warm water bath will do it. In terms of reactions of ethers, we don't really have that many that we're going to go over. The first one that we do, and really that's what we're going to do. We're going to talk about how to make them and how to break them. All right, so the first thing that we did was talk about how to make ethers, specifically symmetric ethers, through this acid-catalyzed reaction of alcohols. We get two alcohols that we're going to join together to create our ether. All right, we looked at our mechanism, and we introduced this idea of these acidic conditions. All right, and we're going to see this a lot, classifying mechanisms as either falling into the bucket of being under acidic conditions or under basic conditions. We're going to first talk about acidic conditions. Under acidic conditions, you're going to have a lot of proton transfer steps in your mechanism, right? So what's playing the role of the proton donor, the acid? Under acidic conditions, it's that hydronium ion. But your base, your proton acceptor, under acidic conditions, we can't have any strong bases. So water will play the role of our proton acceptor. And we see that in our steps of our mechanism here. The first step is to protonate that hydroxyl group to make it a good leaving group. All right, so now we have this good leaving group. Our neighboring alcohol molecule is going to attack that electrophilic carbon, kicking off that leaving group. But now we're left with this protonated ether. So we need to do one more step to get to our product. And again, what's playing the role of the base, the proton acceptor, is going to be water because we're under these acidic conditions here. Cool. All right, so this is how we can synthesize ethers under acidic conditions. We can also break them apart under acidic conditions. So now we're going to talk about our acid-catalyzed ether decomposition. So again, this takes place under acidic conditions, but specifically using one of those hydrohalogen acids. So hydrochloric acid, hydrobromic acid, hydroiodic acid, one of those strong hydrogen halogen acids. Okay, and this will have the effect of decomposing our ether, breaking it up into an alcohol and an alkyl halide. All right, again, we're going to look at our mechanism. And again, we're going to note this is acidic conditions, right? We see that HBr there. That means we got these acidic conditions. Okay. All right, let's see if we can't figure out what bonds we're going to need to make and what bonds we're going to need to break here in this chemical reaction. All right, take a second and list. We'll do bonds broken in red and bonds formed in green. right, what do we got? What's a bond we're going to need to break here? We need this carbon-oxygen bond to break only one of them, right? So on one side of my ether, I'm going to have to break that bond. I'm also going to have to break my reagent bond. Let me be good with my lone pairs here. Between that hydrogen and that bromine. And what bonds are we forming? We got that new oxygen-hydrogen bond, and what other new bond? Carbon and bromine, right? So this is what our mechanism is going to have to do, is break those bonds and create these new bonds over here. Okay? All right, so first step in our mechanism, all right. What was our first step in our previous mechanism? What were we doing here in this first step? What would we call this here? Protonation. Protonation specifically of that oxygen. And this is going to be a really common first step under acidic conditions. We're going to protonate the oxygen in our ether here. If you use hydronium, that's cool. We can use our HBr as well. Either one will work. We just need a proton donor here. All right, on your homework, I specify which one you should be using, just to be clear. So let's do this first step for me here. Protonate that ether oxygen. All right, so one common mistake on your first exam was just the direction of these arrows, all right? So the first unit, we had some mechanisms, but it wasn't crazy mechanism heavy. As we progress throughout the semester, mechanisms are going to become more and more important. The last unit really focuses heavily on mechanisms. So making sure that we can draw our arrows correctly is important, and especially just where your base and where the tip of the arrow is very important. Easy to kind of mess up, but conceptually very important to get down. The base of our arrow needs to be at a pair of electrons. The head of our arrow needs to be at an atom, right? If your arrow is pointed in the reverse direction, it's wrong, right? Base of the arrow here. The other mistake that I would see a lot is something like this, okay? This can also be a pattern that should jump. First of all, it's wrong because of where the base of the arrow is, okay? But even before that, let's say that I gloss over that. I can look at this and tell that something's very wrong here because my arrows are kind of bunny ears outing in different directions. Electrons don't flow in different directions in your chemical reaction. Electrons are always going to flow in one direction, right? So your arrows should kind of line up with one another and be pointing towards the same direction. So my arrows here, if drawn correctly, my oxygen grabs my hydrogen. My next arrow is kind of pointed in that same direction. Your electrons always flow in one direction. So just kind of an easy double check to make sure that we didn't mess anything up. All right, and then if I'm going to draw the product here, another easy thing to mess up are charges. We have those simple bonding patterns that we should be able to recognize. Oxygen, now this lone pair is going to be in this new chemical bond with that hydrogen. So now my oxygen has 3 bonds and only 1 lone pair, meaning it should have a positive charge associated with it. All right, likewise, this pair of electrons between hydrogen and bromine, where did that go? That is now on that bromide ion. So now bromine has not 3, but 4 lone pairs, meaning it has that negative charge. right? And conservation of charges, my net charge in my first step better equal my net charge in my second step as well. All right, so here I'm just kind of coloring these to keep track of what pairs of electrons are what. We have a bond formation occurring, a lone pair becoming a bonding pair, and a bond breaking occurring, a bonding pair becoming a lone pair. All right, now I'm going to tell you there's only one more step here to get to our end product. Everybody take a second and see if you can't fill in the missing electron pushing arrows that would take us from A to B here. Let me get rid of my colors to not be confusing. All right, so now my bromide ion is going to attack my electrophilic carbon here, because now there's this good leaving group, this protonated oxygen, which can come right off, leaving me with my two products, right? So I have another bond formation arrow and another bond breaking arrow to finish off my mechanism. Cool. All right, so we have this acid catalyzed ether decomposition where we're going to take our ether and react it with one of those hydrohalogen acids. This will create an alcohol and an alkyl halide. So in this case, we used this symmetric ether. So there is only one possible option for our alcohol and our alkyl halide. Now let's think about a different ether here, an asymmetric ether. So if we react this with that same hydrohalogen, we got two possible products that would form. All right, so I'm going to keep track of these different segments of carbons here. This methyl group on one side in orange, and this tert-butyl group on the other side in green. Right, so which fragment is which? Okay, so we got two different products. Either we have our methyl alcohol, methanol, and the tert-butyl bromide, or they're reversed, or we have a methyl bromide and a tert-butyl alcohol. All right, you do not get a mixture. There's only one of these two that's correct. So let's see if we can't reason through which one of these is going to be the proper product for this decomposition reaction. All right, and how we're going to explain it is to take a look at that mechanism. All right, so I want everybody to start off our reaction mechanism here, just like we did before, that proton transfer step to kick things off. We're going to look at this intermediate and see if we can't decide which one of these pathways is correct. All right, so here's my organic intermediate, my protonated ether, and I have this bromide ion floating around that's going to be my nucleophile in this next step. All right, and so first of all, what we want to notice is which pathway we get here is dependent on which carbon that bromide attacks, right? If that bromide attacks that orange carbon, that will lead to this pathway here, where I get my methyl bromide. Or that bromide could attack that green carbon, and that would give me this pathway here, where I get my tert butyl bromide. All right? So, looking at these two arrows here, which one of these steps seems more favorable, the red or the blue? Why the red? Yeah, so exactly. Okay, so we already got a bunch of bonds on that green carbon, all right? But why is that going to make that attack less likely? Steric hindrance, exactly, right? Just sheer crowding effects. Which one of these carbons is more accessible? That's really the question here, right? So that's what we want to ask, is which carbon is more accessible? The accessibility of a carbon has a huge effect on its ability to play the role of an electrophile. Can the nucleophile even get there in the first place, right? So because that orange carbon is so much more accessible than that blue carbon, that blue pathway is not going to be the one that occurs. So instead, my mechanism, I'm going to have to finish that off by breaking that bond there. But so my correct pathway here will lead to that smaller fragment being my alkyl halide, and my more crowded fragment being that alcohol. All right, so we can just note that that more accessible carbon gets that halogen. Cool. All right, so we learned that under acidic conditions, if we have an alcohol in the presence of a lot of alcohol in the presence of an acid, we will get this symmetric ether that forms. All right. If we use one of those hydrohalogen acids in the presence of our ether, it will decompose it into these two components here, an alkyl halide and an alcohol. If we use an asymmetric ether, all right, which path is it going to take? Again, we noted that it is not this one here. All right, because of our mechanism, because that bromide has to play the role of a nucleophile. What type of substitution would we classify this as? SN1, SN2? Yeah, everything happens all in one shot here, so this would be an SN2 mechanism. All right, that bromine wants to get to that more, well, it can only get to that more accessible carbon, so we're going to get our halogen on that more accessible fragment of our ether. All right, so we learned how to make symmetric ethers. How would we make something like this an asymmetric ether? All right, this is what's called the Williamson ether synthesis. So let's just get our substrate reagent product combination down here. I'm actually going to make, well, that's fine. And let's actually just note at the very top here, this is our preferable way for making asymmetric ethers. Right? So, our asymmetric ether. First, we're going to treat this with what's called sodium hydride, and we'll talk a little bit more about this here in a second. And then, an alkyl halide. All right? And this will create, and let's just color code our carbons here. This will create this asymmetric ether. This ethyl-methyl ether here. All right, so let's look at our mechanism. All right, so first of all, sodium hydride. All right, we got a metal and a non-metal. So this is actually an ionic compound here. And this is this very weird, very rare charged state of hydrogen. You don't see this too often. Normally we see hydrogen playing the role of a cation. Here it's paired with something that's way less electronegative, this sodium ion here. So actually this is an ionic compound with a sodium ion and what we call a hydride ion, this negatively charged hydrogen. This hydride ion right here is a strong base. Okay, and it's a strong base that's got like one claim to fame. All right, they use it for this purpose all the time, and that is to deprotonate alcohols. All right, anytime you see a sodium hydride in there, chances are that its role is to steal that proton away from that alcohol. All right, so let's see if we can't do our mechanism here. Okay, I want you to draw to illustrate exactly what I was just saying. Use that strong base to deprotonate this alcohol. How would that look in a reaction mechanism? All right, our base of our arrow has to be at a pair of electrons, so that'll be that hydride pair of electrons. We're going to break that bond, giving that pair of electrons to that oxygen. This will create what we call an alkoxide ion. A deprotonated alcohol, now it has that negative charge. What's my inorganic product of this first step? Hydrogen gas, yeah. And so this is one of the reasons why they love to use this as a base, is because what happens to that hydrogen, it just goes flying out into the gas phase, leaving you with just your deprotonated alcohol, right? So a really efficient means of deprotonating that alcohol. Now I got a beaker of my deprotonated alcohol, and there that hydrogen's left. Okay? These things, again, you're going to hear me say this over and over and over again, so let's just note, if we don't already know, this is what's called an alkoxide ion. Not a hydroxide ion, but there's an alkyl chain on it. There's a bunch of carbons and hydrogens, so it's an alkoxide ion. We'll see this thing used as a strong base, but it is also a very good nucleophile. All right, we discussed this as one of our patterns of our good nucleophiles, an oxygen with a negative charge. And so that's what happens, right? We did our first step here, where we added that sodium hydride. Now we're going to do our second step here, where we add in that alkyl halide. All right, and so given what we just discussed about the properties of this alkoxide being a good nucleophile, everybody take a second and finish this mechanism off to give me my asymmetric ether. Oh. I need to form that new bond between my oxygen and that green carbon. So that's what I'm going to do. Nucleophilic attack. Bromide is a good leaving group. And so that's how I finish my mechanism. Cool. Okay, so again, what we're going to see in our mechanism is we're introduced to this new reagent, sodium hydride. Really, the sodium is never doing anything. The sodium's just a counter ion. It's that hydride that's going to be playing the role of a strong base. And in particular, this thing is famous in organic chemistry for deprotonating alcohols, creating these alkoxide ions right here, right? And so that's what we're going to do in the first step, is create that alkoxide ion. That's then going to be a strong nucleophile with my electrophilic alkyl halide. All right, attacking that electrophilic carbon, kicking off that bromide leaving group. Okay, if we want to be good with our charge balancing, we can see it's that negatively charged bromide ion that gets kicked off. leaving us with our organic product, our asymmetric ether. All right, so now let's say that we want to create, our goal is to synthesize this asymmetric ether. This thing right here, tert butyl methyl ether. All right, again, we're going to kind of color code our fragments here so we can keep track of who's who. I'll have my green methyl, my orange methyl, and my green tert butyl fragment. All right, now in theory, there could be two combinations of reagents that we could use. We could use a methanol, a methyl alcohol, treat that with sodium hydride, and then add in that tert butyl bromide. That would be one way to get to my product. Okay. Or I could start out with this tert butyl alcohol. Treat that with my sodium hydride, and then bromomethane. All right, so in theory, we could use either of these two combinations to create our asymmetric alcohol. Pencil and paper-wise, they both seem to be equivalent. All right, however, if you were to actually do this in the lab, one of these is going to be way more efficient than the other. One of these would be the proper way to do it. All right, so let's see if we can't figure out what's what here. All right, we're going to do kind of a split screen of our mechanism here. Okay, let's draw the product of that first step. We'll call this, let's go A and B. You're going to be A, you're going to be B. Let's draw that product of our first step in our mechanism, that alkoxide ion, for each of these two scenarios here. I'm actually going to do the mechanism. Let's see if we can make a point here. Okay? So that first one, my product of that first step would be that methoxide ion. And in the second one, the product of that first step would be that tert butoxide ion. All right. If we look closely at this mechanism here, do one of these look more favorable than the other one? All right. So we sort of have been talking about this steric argument here, but importantly, how big is this hydride ion going to be? Is that a big thing or a little thing? That's about as teeny tiny as you could possibly get, right? A single hydrogen atom with an extra lone pair, that doesn't really have the same limitations on where it can travel in solution because it's so teeny tiny. Not only that, but this oxygen is sticking out at the end of the molecule. It's not buried in the middle here. So in terms of this first step here, neither one of these is more favorable than the other one. Sodium hydride would do a great job of deprotonating either one of these alcohols. It's frequently used to deprotonate any alcohol. All right, so first step in our mechanism, we can't quite distinguish what's what. So now let's move on to the second step of our mechanism here, that nucleophilic attack step. All right, so now we're going to draw in our nucleophile. So this is now our second step. I'm sorry, we're going to draw in our electrophile. All right, that second step in our mechanism. All right, which one of these is going to be more favorable, A or B? And why B? Same argument. Steric hindrance, we have our more accessible carbon. Right? That alkoxide ion is going to have a much easier time attacking a methyl carbon than it will attacking a tertiary carbon. All right, so in terms of our pathways here, A and B, one of these is much more preferable than the other one. If we're trying to synthesize this alcohol here, we're not going to choose this top path here. We want that electrophile in our reaction, which is that halogen, alkyl halide carbon. We want the more accessible carbon with that halogen. All right. Now, fortunately, in terms of things we have to keep track of in our head, that is very similar to our acid ether decomposition reaction, right? Again, we wanted that more accessible fragment on our halogen. Same thing if we're going to synthesize an ether using this Williamson ether synthesis method. We want the more accessible carbon to be with our halogen. That's going to lead to the most efficient reaction. All right, so we got these three reactions of ethers. First of all, how to make them in the presence of an acid. Then we figured out how we can decompose them in the presence of an acid. And then finally, if we want to make an asymmetric ether, we're going to use this Williamson ether synthesis that uses that sodium hydride to make a good nucleophile, an alkoxide ion, and then follow it up with an alkyl halide. Cool. All right, we're going to end there a little bit early. As I said in my announcement, a few of y'all forgot to put your name on your exams. All right, so if you got a 0 on your exam and you're like, wait a minute, I hope that's not true, please come up here and claim your